Pragam Prabha. Digital India. Educated India.
Okay, so very good morning to all of you. Today we will discuss. So far we have discussed many data structures in this course. So today we will talk about a design technique. So now we'll move to the algorithm part, and we'll start the graph algorithm. So before that, we will discuss one design technique. We have done one design technique, if you recall, that is the divide and conquer technique for dividing the problem into sub-problems of lesser size. Then we conquered those sub-problems by solving them recursively. Then we combined those sub-problem instances to get the solution of the whole problem. So that was the divide and conquer technique we have discussed. So this DP or dynamic programming is a similar technique like divide and conquer technique with a. So we'll know what is DP through an problem, through an example. So that problem is called longest common subsequence problem. So let us first talk about what is the longest common subsequence problem or LCS problem. Then we'll slowly move to the this design technique, which is called dynamic programming or DP. Okay, so what is the longest common subsequence problem? The problem is, suppose you have given two sequences, x and y. X is of length m and y is of length n. Then you have to find a longest common subsequence. A or the, if there is only unique subsequence longest common, then that will be the. So that is the problem for today. So for example, if we have a x sequence like this, these alphabets A, B, C, D, A, B, C, B, D, A, B. So this is our x sequence, and this is our given y sequence B, D, C, A, B, A. So we want to find the common subsequences of maximum length, longest length. We want to find the subsequence of long. Suppose AB is a subsequence, because AB, if you take just AB is a subsequence of x. Also, AB is a subsequence of y. So, sorry. So AB is a common subsequence of both x and y. What is the length of this subsequence? Length is 2. Now we are interested to see whether is there any subsequence of length more than 2, length 3. So we can check that, like BCB. If you take this subsequence BCB, if you take just BCB, so this is a subsequence. This is a subsequence of length 3. We want to check whether this is a common subsequence. Yes, this is subsequence of this A, and this is also a subsequence of this is subsequence of x, and this is also a subsequence of y, because this is B. So B, C, B. So this BCB is a common subsequence of x and y of the given sequences x and y. So this is a longest common subsequence of length 3. We can have other common subsequence of length 3 also, like we can have, say, ABA. So if you so ABA, so A is here, A, B, A. So ABA is a subsequence, common subsequence of both x and y, and that is of length 3. Now we want to see whether we can have a subsequence. So because we are looking for longest common subsequence, so we want to see whether we can have a subsequence of more length, like length 4. So for that, let us try that. So length 4, we can check whether we can have it or not. So we can take a subsequence like BCBA. So BCBA. So this is a subsequence of A, and also this is a subsequence of B. So BCBA. So BCBA is a common subsequence of both x and y. I mean the given two sequence. So BCBA is a subsequence of x and y. So is there any other subsequence of length 4? This is of length 4. So we can check that. even we can have like A, yeah, B, any other,
BDAB.
BDA. CAB.
yeah, B, D, A, B. So B, D, A, B, yeah, B, D, A, B. So that's why it is a longest common subsequence. So it need not be to be unique. So, but the question is, this is of length 4. So we can quickly check whether we can have a common subsequence of length 5. Then that will be the longest common subsequence. But you can easily verify that this two, given these two subsequence, we have only the longest common subsequence is of length 4. But there are many subsequence we can get of length 4. So that's why we are interested to have a longest common subsequence, not the. But length is unique. Length of this the longest common subsequence length, here it is 4, that 4 value is unique. So that is an observation we will use there. Okay, now so this is our problem for today. We want to find, given two sequence x and y, we want to find the longest common subsequence between these two sequences. Now, what is the naive approach? What is the brute force method? Any idea how we can solve this before move to the some DP technique? Any naive approach you can suggest?
So I suppose the naive approach would be to see like all the possible subsequences in X and then checking whether they're present in Y.
Yeah. So yeah, that is the idea. So we take all possible subsequences of X. So X is a set of size M. So the power set basically. So 2 to the power M subsequence are possible. So we take a subsequence, then we check whether this is a subsequence of Y or not. So that check will cost us how much time? So what is the total time complexity for this? How much time will spend to check one given subsequence whether this is a subsequence of Y or not? Y is of length n, so maybe we need to scan the Y, like you can put it into array. So this is for checking only one subsequence, whether this is a subsequence of Y or not, will cost us linear time in n, and there are 2 to the power m such subsequences. So it will cost us 2 to the power n into n, order of that. So exponential. So checking each subsequence will cost us order of n, because this Y size is n, and there are 2 to the power m subsequences. This is the power set. A kind of bit vector. One bit is present or absent, something like that. So worst case runtime is for this is n into 2 to the power m, which is exponential time. But we want to do it something more faster way. For that, we will just introduce this dynamic programming technique. So for that, let us simplify this problem. So our problem is to find a longest common subsequence. So instead of that, if we find the if we can find the length of the longest common subsequence. For our given example, it is 4, and that length is unique. So if we can first find the length, that 4, and then after that, if we can extend that algorithm to find a longest common subsequence, that is the idea. That is what is called sorry, what is called simplification step. So first we first look for the length of the longest common subsequence, and that length is unique. So once we get the length with some algorithm, we'll discuss. Then we extend that algorithm to find a longest common subsequence from the length of the, after getting the length. So that is the idea, that is the simplification. Okay, so we denote the length of a sequence by this mod, whatever you represent this. So length of a sequence we represent by this box, like mod symbol. So this is, if x is a sequence, then this mod of x denotes the length of the sequence. Yeah, so we just consider some prefixes of x. So x is a sequence of so x is a sequence of, what is the total length of x 1 to m, 1 to I, then we have dot 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 m. M is the size of x sequence, and similarly we have y sequence which is starting from 1 to, and we have I, j over here, some general index, some index up to n. So we have two given sequence. Now we want to define some Cij. So Cij is nothing but we take two sequence x and y, but x is from 1 to I, so we take up to this. So we take two sequence x is from 1 to I, which is a subsequence of x obviously, and y is from 1 to j, j is greater than I. Anyway, these two are just a variable, two variable index anyway. So now we take two sequence x up to I, y up to j, then we find the, we consider the Cij to be the length of that longest common subsequence of these two sequence x and y. I mean these two sequence up to I, up to j. Is this notation is clear? So we just take a subsequence here, x is instead of up to m. So if I is m, then it will give us the full sequence of x. If I is j is n, it will give us the full sequence of n. So we are just considering some prefixes of x and y. So we take x up to I, we take y up to j, and then we consider the longest common subsequence between these two x and y up to I, up to j, and then the length of that subsequence will be Cij. Now if we can find all Cij's for all I and j, then we are done. Why? Because what we are looking for? We are looking for length of the longest common subsequence. So can you tell me what is in terms of Cij? What is that?
So I suppose it will be the length of the longest common substring up to Cij, and then after Cij up to like m in x and n in y.
Yeah,
So
I is equal to m and j is equal to n, because suppose we get some so I is varying from 1 to m, j is varying from 1 to n. Suppose we can, some algorithm can give us all the possible values of Cij. Suppose we will discuss that. Then from there we are done, because we are looking for the mn basically, because that will give us the x is from 1 to m and y is from 1 to n. So that is the idea. I mean that's why we break it into prefixes. Like if we can start with some I lower value, if we can some bottom up method or some way, we'll discuss that to get the upper values of I and j slowly, and then we can finally get the Cmn. That is our ultimate goal. Our ultimate goal is to find the longest common subsequence of the whole sequence, not the that x is I and y is j. Is this okay? So if somehow we can get the all possible Cij's, then we are done, because we are basically looking for Cmn. So that we have to get. So from some way, some technique, we have to achieve that. We have to start with some lower values of Cij's, and slowly we should build up the matrix, because Cij is, if Ij is varying, this is nothing but a table of size m into n. So you can consider as a matrix, whatever you feel. So basically we want to sorry, get some algorithm to find the all Cij's. And why we are looking, and why we are done, because once we get all Cij's, then from there we can get the Cmn, and that is basically our we are looking for. We are looking for length of the longest common subsequence of whole sequence x and y. So that is our Cmn. That is the length of the longest common subsequence of whole sequence. Okay. So now for that, for this type of problem, we usually write some try to get some recurrence in this Cij's. If we have some recurrence, then we can use the recurrence in our algorithm. So for that, let us have some theorem. How we can write Cij with the with the lesser index. So that is the called recursive formulation of this. So every DP dynamic programming, if we want to apply, we should have this type of recursive formula. Otherwise, we cannot go for that. Anyway, so our claim is Cij can be written as Ci minus 1 comma j minus 1, one index less, plus 1 if xi and yj's are same. Otherwise, it is maximum of Ci minus 1 comma j, this value, I mean whichever is the maximum, this value or this value. So everywhere it is with the less index, because this is I and j, and here it is I minus 1 j minus 1, here it is I minus 1 and j less or same index, and here it is I comma j minus 1. So either we will go for one of this formula depending on this fact whether xi equal to yj or not. So that will give us an algorithm to calculate the Cij's. Okay, so how to prove this? I mean, this is a theorem, or this is a lemma, you can say. This is a claim. You need to prove this claim. Why this is true? Okay, we'll just try to prove this. We'll prove the first part, and second part will be very much similar with that. Okay, so now this is our first case 1, when this, so we have two sequence, x sequence, y sequence. Now we consider two index I and j. So this is two index I and j. This is xi, the value over here, whatever, and this is yj. So now in the first case, if we assume these two values are same, if here is a, here will be a, if we have alphabets like that. So these two values are same. If these two values are same, then we are claiming that Cij can be written as Ci minus 1 comma j minus 1. That means if we consider the x sequence up to I minus 1 and the y sequence up to j minus 1, then if we consider the length of the longest common subsequence of these two sequences up to I minus 1 up to j minus 1, then that length, if we add with 1, then that will give us the Cij, length of the longest common subsequence up to I up to j. So that is our claim. But how to prove that? So that we have to see. Can you visualize the proof? So this is our I minus 1. Just the one index less, and this. Yes, please. Any idea why it is true?
Here we have xi and yj are same, so we have already one common length. So 1 plus the I minus 1 plus j minus.
Okay. You mean to say whatever value over here, suppose this is z, now this will also be z. That is the assumption, because this is the thing. So yeah, but intuitively you are correct, but we need to have a proper proof for that. So for that we will use the sum. Yes.
Sir, so when we have found out, like now we are finding out Ci comma j, but when we have already done Ci minus 1 j minus 1, so we have already found out the longest common subsequence in that. So we already know what is the longest common subsequence, and now when we get a common character at I comma j, so we can say that this is our new longest common subsequence.
Yeah. So so in your logic, in that case, we have to prove that we have to convince that this z will be z must be in the longest common subsequence of this x and y up to I and up to j. Yeah, you are correct. But that proof we need to do that this z, this common symbol has to be in the longest common subsequence of x and y, where x is up to y and y is up to j. Yes. So that proof is required. So yeah, so let us try to prove that. So suppose length of the longest common subsequence of this is say k. So this up to I and up to j. So that is, suppose length is k, and this is our this is a longest common subsequence z1 z2 up to zk. And now we need to prove that zk, whatever this z value is over here, zk is nothing but this common value. If we can prove that, then you are correct, because if we have a some subsequence over here, then this will be the part of that we can include that. So that proof we need to do. How to proceed? Yeah, so we take a longest common, suppose length of the longest common suppose Cij is k. This is the assumption, Cij is k. We are assuming that Cij is k. Suppose length of the longest common subsequence up to I up to j in the x and y respectively is k. So now let us, so that means that there will be a subsequence which is of length k. So suppose this is one of them, z1 to up to k, and this is capital Z, which is just zk, the last one. And we are claiming that this this is the last one, zk. We are claiming that this zk value has to be this common value. Why this has to be this common value? The last again you can prove this by contradiction. Suppose not. Suppose this zk is not this this common value. That means we have a subsequence of length k without considering this last value, which is common to both of them. Then we can concatenate that with that z sequence up to k with this z value, new z value, and that will give us a longest, that will give us a common subsequence between x and y up to I and up to j respectively. But the length of that sequence, when you concatenate with this with z, length of that sequence will be k plus 1, which contradicts the fact that Cij is k. So that is the proof of our argument for this the last point of this common value. Okay, so that means yeah, so that means this Cij. So far we have proved only this zk is this common value xi or yj. Now but we have to prove this. We have to prove this. To prove this, if we can show this zi to k minus 1 is a longest common subsequence of these two, then the length of this longest length of then the ci minus 1 j minus 1 will be k minus 1. Then we are done. This z of just this is 1. Sorry, this is 1 2. This will be 1. So z1 to k minus 1, if we just ignore this last element, this is a common subsequence of x I minus up to I minus 1 and y up to j minus 1, because that's why this is the longest common subsequence of x up to I up to j. Now this is a common subsequence. Now we'll prove that, we'll argue that this is a longest common subsequence. How to show that? Any idea? If we can do that, then the length of the longest common subsequence up to I minus 1 up to j minus 1 will be just up to I minus 1 up to j minus 1 will be just k minus 1, and then with this plus 1 will give us k, and that is the proof. So that is the thing. So how to prove this? Any idea? How to prove this? You got my argument. We have to show, we know that z1 to k minus 1 is a common subsequence, because we are just omitting the last value, which is xi yj. So now we take this, so this has to be a common subsequence of up to this, and this has to be also common subsequence up to this. Now the question is, we want to show that this is longest common subsequence, not only common subsequence. Why?
So we can begin by assuming that I minus 1 up to I minus 1 and j minus 1, it is the best common or the longest common subsequence. So then, like when we come to the ith and jth element, if they're equal, we're adding 1, because that means that the longest common subsequence includes that element. But if after including the ith or the jth element, it is not the best optimum subsequence, then it means that the previous one was also not the best. Which, I mean, it's a contradiction that way.
Yeah, yeah. So if we assume this is not a longest common subsequence, this is a common subsequence. So if we assume this is not a longest common subsequence, that means we should have a common subsequence of length more than this, because this is a subsequence. So if it is not longest, then that there will be a subsequence which is having length more than this. So length more than this means this is of length k minus 1. So we should have a subsequence whose length is k, which is so in that, with that, if we add these two, add this common value, then we have a subsequence of length already k and then plus 1, k plus 1, which contradicts the fact that Cij is k. So that is the argument. So we are arguing based on the this contradiction. Okay, so that is the proof. Yeah, so this we have already discussed over here. So this is our Cij, a longest common. So this, yeah. So this proof we just cut and paste technique. So we assume this W is a longest common subsequence. So that length of the W has to be k, because this W is this is a, that Z is a common subsequence. So if the longest common subsequence is not this one, so then there has to be a subsequence, common subsequence, whose length is more than this. So more than this means at least it will be k. So now if we concatenate with that last value yxi and yj, so that will give us a common subsequence of the whole, I mean up to x up to I, y up to j. But that is not possible because length of this common subsequence is k plus 1. But we have assumed that length of the common subsequences of up to I up to j is k. So that means the contradiction. So this has to be a longest common subsequence of this x up to I minus 1, y up to j minus 1. So length of this is k minus 1. So the C of I minus 1 comma j minus 1 is k minus 1. So then k minus 1, then C of, what is C of I comma j? It is k, which can be write as k minus 1 plus 1. So k minus 1 is C I minus 1. So that is the proof. Okay. So other case means this part, this max part is very much similar with this. I'm not going for that. So that is the proof. Anyway, so now now we want to go into the algorithm part, like dynamic programming approach. So there are some hallmark, there are some indication that for a given problem whether we can we can go for DP or not. So basically we'll discuss two hallmark for this. One hallmark is this was first one. This is telling the optimal substructure. What is the meaning of that? This is telling an optimal solution of a problem contain the optimal solution of the sub-problems. For example, here we know if Z is a longest common subsequence of x up to I minus I and j, then if you take any sub up to j up to k minus 1 will be the longest common subsequence of up to I minus 1 j minus 1. So that is the any solution has contained the solution of the sub problems. So an optimal solution of the problem or problem instant contain the optimal solution of the sub problems, because if we have a longest common subsequence of that z 1 to k is for sequence up to I and j, then it contain the longest common sub, because up to k minus 1 will be the longest common subsequence of up to x minus 1, y is up to j minus 1. So that is the indication, because our problem, our this Cij is having that indication that okay, so we have this property, that optimal substructure. That means if we have a solution of this of a problem, then it contains the solution of the sub. From there we can get the solution of the sub problem. So this is hallmark number 1 for DP. Yeah, so because this, if z is the longest common subsequence of x and y, then any prefix of z will be the longest common subsequence of prefixes of x and prefixes of y. Okay, now we are going to use this this theorem or lemma in an to have a recursive algorithm, because we want to get Cij for all I and j. Ultimately, we want to get Cmn. So this is a bottom up technique. Okay. So what is the algorithm for that? Now algorithm will comes from this recursive theorem. This theorem will give us the algorithm. Yeah. So let me erase this. So yeah. So this theorem is basically is our recursive algorithm or formulation. So this theorem is telling Cij will be equal to Ci plus I minus 1 comma j 1 index less both the x and y, and otherwise if it is equal, if xi and yj are equal, otherwise it has we have to calculate this Ci minus 1 comma j and Ci comma j minus 1. So max of this two will be the will be our Cij. So this will use for the theorem. I mean for the algorithm. So we are basically this is our pseudo code. We are basically finding the LCS of, this is actually length of the longest common subsequence, Cij's, as we want to find Cij. So this is the this is the call. This is the call. We are going to get the Cij. So this is number one. So now if xi, we check whether xi equal to yj or not. If xi equal to yj, then the formula is telling it is Ci minus 1, j minus 1 plus 1. Okay. Now if xi is not yj, else if this is not true, then we have to calculate two recursive call. We have to calculate Ci minus 1 comma j and Ci comma j minus 1. And among these two, whichever is the maximum, that is our Cij's. That is our Cij. So either one of these. So if we are in the worst case, we have to go for this else part. In the worst case, we have to have two calls, this Cij, I minus 1, j minus 1, and then we have to get the maximum to have the Cij's. So now the thing is, if we are lucky, then I mean the best case is if we are lucky, then we have this equality, xi will be yj, and then we have this formula. So in that case, we have only one call, only one recursive call. We have to get the Ci minus 1, Cj minus 1. Otherwise, in the worst case, we have to go for two calls. Then we have to get the max among these. So this is the pseudo code. Now, worst case scenario, as I said, is when they are not equal, when the else part will occur, which case the algorithm execute two sub problems. We have to have two calls with a less parameter, only one less. But here we have, if we are lucky, then this will be equal, and we have index less in both the place. So that is the size is also reducing in both the index, but here size is reducing only on one index, either in I for this call and for this call in j. So that is the worst case scenario for this. Okay, now let us draw the recursion tree for this worst case scenario of this code for some value. Suppose we are looking for C3, 4. Our we are looking for C3, 4. Our x is of a sequence of length 3, y is a sequence of length 4. We want to ultimately get the value Cmn. So m is 3, n is 4. So now we are in the worst case. So that means we will not have always xi equal to yj. So for that we need to have two calls. One call will be Ci minus 1 comma j, and then another call is Ci comma j minus 1. So again on this call we have to again call. So we are in worst case scenario. This is the worst case recursion tree. So again we have to have two calls. One index less over here. So 1 4, and this is 2 3 like this. So here also 2 3 3 2 like this. So this way we continue like this. So this is the height of this tree is m plus n. But if you look at here, there are lots of repetitions are going on, because in this part same sub problems. If we calculate 2, 3 here, then again here we are calculating 2, 3. So there are lots of repetitions are going on, because once we calculate C2, 3, why to calculate again? So somehow if we can memorize that in a table, so that is the idea of dynamic programming technique. We are going to memorize this value once it is calculated. That means we are going to check whether that value is available or not, because in this branch we are calculating C2, 3. For that we have to calculate this. Again if we come to this branch, when, because this is a sequential calculation, sequential, our algo course is sequential, I mean not parallel computing. Okay, so again once we come here, again we have to calculate this. That is the so if we somehow memorize this, if we somehow store these values in some table or some array, then we can use here, or if we do it first here, then we can use here. So that is the idea of, so that means this is the second hallmark. We have many repetitions of the sub problems. So this is the hallmark number 2. Then when we think for, okay, this is the time for applying the DP for our problem. So this is the second indications or second hallmark, that overlapping sub problems. A recursive solution contains a small number of distinct sub problems repeated many times. So if we see that in our problem, then we should think for, okay, I think this is the candidate of DP. So we must apply the DP. Okay, these two hallmarks are for the dynamic programming technique to be used. Let us do the memorization algorithm, memoization. Okay, so the idea is, once we compute this C value, we'll just not recompute, we just check whether it is computed or not, then we store into the table. Once we compute a solution, once we compute some values of C, we store into the table, and then in the subsequence call we first check the table whether it is there or not. If it is there, we will use that instead of avoiding the recomputing. Any question? Okay, so let us write the code for this introducing the table or introducing the memorization method. Okay, now code is very much similar. Only thing we want to check whether we have calculated or not. So we just start with we are finding Cij. So for that we check whether we have calculated this or not, whether this is present in the table or not. So nil means we have not done yet. I mean, this is, we have to calculate. Okay, so now if it is nil, that means if it is not available in the table, then we have to calculate it. So for that we have the recursion theorem or recursive formula for that. This is same. If xi equal to yj, then we have this formula. Otherwise we have this formula. Okay, so this is the memoization, and the time complexity will be order of m. We will take an example, then it will be more clear. Order of m into n, and space will be m into n. Let us take a quick example of our given to sequence to have the longest common subsequence. Oh, okay, first of all, length of the longest common subsequence, that is the simpler version of this problem, and then after getting the length, we will go back to the to find a longest common subsequence. Okay, so let us just start with this. Can you please mute your mic? It is having some noise. Otherwise, I can. Somebody's mic is on, so yeah, I am just muting all. Yeah, so basically we have two sequence x and y. If you remember, that sequence x is a b c b d a b, and y is b d c b d b d c a b a. So this is x sequence, this is y sequence. We are going to find the longest common subsequence between these two. First of all, we want to get the length of the longest common subsequence. Okay, so now these are the Cij's values. So we want to put the Cij's values over here. Now this is so y is not started here. So this is C of, this is C00. This value is C, this table is for Cij's. So this is C00. C00 means there is no X sequence started, there is no Y sequence started. Obviously C00 will be 0. Now this is C01. Y sequence C10. So 1 means we have only one Y X sequence, but there is no Y sequence. So there is no question of longest common subsequence. There is no question of common subsequence because Y has not started. So this part is C20, C30 like this. So this is the 0th row of Cij, and this is the 0th column. Similarly, here where X sequence is not started, this is C00, this is C01, this is C02, like this. So this will be all zeros because there is no question of longest common subsequence because one sequence is not yet started. Now this will be what? This will be C11. So how to get C11? This value? Any idea? We have to use the formula. We have to use that algorithm. This is the bottom-up method. So we have this lower values of Cij's. Then we have to use this. Yeah. So So this is the code. So we have some lower values of Cij's. Then we have to use this algorithm to test whether these two are same or not, Xi and Yj. Then Cij will be Ci minus 1 j minus 1 plus 1. If Xi and Yj is not same, then it will be Cij will be max of Ci minus 1 comma j comma Ci comma j minus 1. So this is the formula over here. So now we want to find C11, this guy. So C11, for that we have to check whether these two values are same or not. So this is x1, this is y1. These two values is not same. So then in that case, this is the worst case. Worst case means maximum of C01, C10. So maximum of these two. So these two are both 0. So max will be 0. So this is 0. Now come here. This is what value? This is C21. This field. We have to get C21. So for C21 again we will go for the algorithm. So C21 will depending on these two value. X2 is B, Y1 is also B. So these two are same. So then the formula is it will be C21. So C10. So this plus 1. So this will be whatever value over here plus 1. So this is 0. So it will be 1. So this will be 1. This is because these two are same. We are using that. So this is the lucky case. Okay. Now here again we proceed. For this we need to check these two value. These two value is not same. So in that case, worst case, we have to get the maximum of this and this. Maximum of this is 0. This is 1. Maximum is 1. So this will be 1. Similarly, these two are same. So this Cij will be Ci minus 1 comma j minus 1 plus 1. So that is the Ci minus 1 j minus 1 plus 1. It will be 1. 0 plus 1, 1. So that is 1. So similarly, we proceed to the first row. We get the field of the first row. Now start with the second row here. Similarly, so this is C12. C12. So for that we need to check this value and this value. This is A, this is D. So these two are not same. So it will be maximum of these two. Maximum of these two is 0. So we put 0 over there. Now again these two are not same. Maximum of 0 and 1. This will be 1. So like this we continue. So now come here this Cij. So we check these two values. These two values are same. Both are D. So that means we are lucky. So we have to only one call, that is Ci minus 1 comma j and Ci minus 1 j minus 1 plus 1. But Ci minus 1 j minus 1 we don't need to calculate it again recursively because we already calculated and we store it. So that is called memorization idea. So we just memorize that, we just store it in order to avoid the recalculation. So that is the DP technique. So these two are same, so this value will be the C I minus 1 j minus 1, this is 1 plus 1, so this is 2, so this will become 2. Similarly, this is for this field, we have to get these two value, this is A, this is D, not same, so we have to get the maximum of these two, maximum of these two is 2, we put 2 over here. Similarly, these two, 2. We will continue with this, like this. So, very carefully we need to get this. Okay, so now here, so yeah, suppose here, just another example, suppose here Cij, this is our Cij, so we need to compare, this is xi, yj, these two are not same, so this will be maximum between these two. So these two are 3, so maximum is 3. So we already have this value, we don't need to calculate again recursively, we are storing these values. So that is the memorization, that is the DP. Okay, now this value, so we have this equality with the B, so we just get the Cij with this value which is already stored, we memorize this plus 1, this is 4, so this will be 4, we got 4. And why we are making this line, we'll come to know, because this is to give us the length. Now after getting the length, we should get back, we should able to get the sequence which is having this length. So to create the sequence, we have to follow this arrow, I mean this line, so that's why we are putting this line. Anyway, I'll come to that. Let me complete this table. Okay, so we can just continue like this, Cijs. So finally, what is our CMN? Done. What is CMN? What we are looking for? We are looking for length of the longest common subsequence of x, whole sequence x up to m, and y up to n. So in terms of Cij, so this is our Cij table. We have calculated all the Cijs, bottom up way, memorization way. Now what we are looking, what is our output? What we are going to output?
CMN.
Come on, what is our result? What is the CMN? This 4, this last field. So this is our CMN.
Box.
So that is the length of the longest common subsequence of the whole sequence x and the whole sequence y. Any questions? Somebody is calling. Okay, so yeah, so yeah, so now we got the length. So this is our ultimate. This is our this guy we are looking for. This is our CMN. CM comma n. So length of the longest common subsequence of two given sequence x and y, full sequence. So this is our output. Now we got the length by this bottom up method or DP method. We got the length. Length is 4. Now the question is, we want to get a subsequence of length 4. I mean common subsequence of length 4. So for that we need to follow the arrow. So we can follow like this. We can, I mean there are many ways we can do this, because there are many longest common subsequence. This is not unique. So we can get this. So for this B is the common. So B we can write. We can take this path. So for this it is A, and then we can either go for yeah, we can get this. This is also B or this. Anyway, so this is no. Am I making mistake? So this part is for. Let me just repeat it. Let me just, okay, so we can follow this. So if we take this path, so it is A is common. No, we want to take anyway, I mean this is A. If we take this path, we take A, then if we take this one, then this was common was B or A? Yeah, B. B. Then if you take this one, this was C. And then if you take this one, this B. BCBA. BCBA is a common subsequence of these two. If you take this path also, you'll get different subsequence. So this is the idea. So idea is to follow this after getting the longest length of the longest common subsequence. We can follow this path to get the longest common subsequence. So this is what is called dynamic programming technique. We have basically two hallmarks. We have the indication that okay, this is the time to think for DP. So these two hallmark we'll see whether we can get for our problem, so that we can think for applying DP. This is the bottom-up method or memorization method. So what is the time complexity for this? So we have this, we have to make this table. So to make this table, we are memorizing. So we don't need to go back again to calculate. So it is basically order of size of this table, m into n. Okay. So this is the backtracking we did. I have already discussed this. Yeah. So BC, BA. Anyway, you can have another way of you can take another path of backtracking. You will get different. Okay. Any question before you stop? What is the space complexity? Is same, which is please.
Sir, we constructed the table in time of order m into n, but when we like reconstruct or we backtrack it to find out the actual common sequence, which is the longest, it will also take some time.
But if we can store this backtracking information there, we can save that time, right? If we can store this this thing, like because length, that will be, I think, if the length is k, that will be, I think, order of k. Reconstruct by, yeah, you are correct. So backtracking, for backtracking, it will take some time, yes. But that
so
will
sir,
not.
I mean to ask that in the pseudocode which we have seen till now, we have not done this backtracking in that code.
No,
we
have
have to
not
make
done
some
backtracking.
changes.
Yeah, we have not done the backtracking because we simplify this problem into instead of finding the longest common subsequence, we want to find the length of the longest common subsequence, and that can be handled by DP. So now once we get this length, then we can do this backtracking to get the a longest common subsequence. Yeah, you are correct. Okay, so now we'll next we'll start with the what is called graph algorithm. Not today. So next class we'll just start with the graph algorithm. So there will be some more algorithm will coming. So far we have discussed many data structure. We'll just now concentrate on the algorithm part. So in there we'll discuss another technique which is called greedy technique, which is also powerful technique for design technique. So we'll see that in the next class. Okay. Thank you.